Heyo, it's Mr. Otwell, the Math Master, helping you master math, and today we'll be solving some equations with logarithms in them. In another video, we'll be solving using inverse operations, but I want to give you two options and then you can just choose whichever one you like better. You could leave a comment down below. Which way do you like? Which one do you prefer? If you like this video, give me a like. You could subscribe down below as well. Let's do this. So we want to solve some logarithmic equations. I feel like a good way to start doing this is just to kind of use the ABX method that I mentioned in my logarithm property video. If you want, you can go check that out. It lays that foundation you'll need. I'll put a link down in the description. Basically, we want to kind of use this idea here. We can change any logarithm equation into an exponential equation. Once we can just get a logarithm, then switch it into exponential form, we're like good to go. So let's see how that would play out here. We have log base 2 of x equals 3. We want to go from log form to exponential form. So we need to identify b, a, and x. So in this case, our b is going to be 2 because that is our base. So b is 2. Our a is the number that's in the log, or whatever's in the log. In this case, what's in the log is x. So our a is x. And then our x is whatever's on the end of the logarithm, on the other side of the equation. Anything over here. So our x is 3. So we're going to take the a, b, and x we found from log form and turn it into exponential form. B to the x equals a. So the b that we found is 2, so we substitute 2 in for our base. Our x is a 3, so we substitute that in there for x. And then our a is just x. So from here, dude, we're basically done, right? X is equal to 2 to the third. And we know what 2 to the third is, so we're going to go ahead and evaluate that. So we know that x has to be 2 to the third power. 2 to the third power is just 2 times 2 times 2. So that gives us 8. 2 times 2 is 4. 4 times 2 is 8. So we know that x must be 8. So log base 2 of 8 equals 3. And if you remember back to the definition, that just makes sense. Remember, log base 2 of whatever that is asking 2 to what power is what's in the log? Well, there it is. 2 to the third power is equal to 8. So our x needs to be 8. In that first equation, we were solving for something inside the log. And as I showed you, we can just substitute a, b, and x. And usually that kind of gives us insight into what x would be. If we need to get something out of a logarithm, moving it into exponential form will directly give you that solution. If all that's inside is x, it's just going to straight up give you the solution. In this case though, log base what of 64 is 3. Well, let's put it in exponential form and it will help us shed some light on this solution. So our b is our base is x. Remember, we can find b by looking at the base, and we know that it is x. A is what's in the logarithm, the argument. So in this case, our a is 64. And x is what the log is equal to. Our log is equal to 3. So our x is 3. Just as a reminder, you probably noticed it over here, but this x here and this x here are different. This x is from the equation. This x is from our forms here. So make sure you're not getting too mixed up. Basically, all the variables that I'm putting on the left are all the variables from up here. And then anything we write on the right side is all from our equation. So same case here. A, b, and x are coming from log form. And any of these values here are just coming straight from our equation. So now that we have everything ready, we want to move from our log equation to an exponential equation, because log base b of a equals x is the same as b to the x equals a. So b in our case is x. So we're going to say x here for our base. Our x is 3. So we're going to substitute a 3 in right there. And our a is 64. So we substitute 64 in right here. So at this point, we don't have just a solution. We just have another equation that's written, honestly, just in a little better of a form that we're just a little more comfortable with thinking about. So now we're saying the equation itself is x to the third power equals 64. So what we're asking ourselves is, what do we need to have as the base so that when we raise it to the third power, when we multiply by itself 3 times, we're going to get 64. Well, we could do a little guess and check here. I'm going to make another video right after this about solving these exact same equations using inverse operations, and that one's just going to do everything you need to every single time. You just have to be a little more comfortable with inverse operations, but the method I'm showing you now requires a little bit of number knowledge and being a little comfortable with that kind of stuff. So if that's something you struggle with, you may just want to go check out the inverse method that I'm going to show, and that might be more helpful. I just want to give you 2 different ways so that whichever way is most helpful given the situation, you have a bunch of tools in your tool belt. So we're asking, what to the third power is 64? Well, we already wrote up here, we know 2 to the third is 8. So x can't be 2. The base can't be 2. Well, what about 3? Let's just check the next one, right? 3 to the third power is 3 times itself 3 times. 3 times 3 is 9, and then 9 times 3 is 27. So it didn't give us what we want, so our base can't be 3. What if we check 4? 4 to the third is 4 times itself 3 times. 4 times 4 is 16 here, so we have 16. 16 times 4 is 64. Now, hey, look, we're trying to make something get 64 when we raise it to a power. So we now have figured out our base has to be a 4. This value right there has to be 4 in order to make this equation true. Therefore, x equals 4. And that's our solution. So here's another example. We don't know what's in the logarithm. So as we found here, if we just convert it straight into exponential form, we're just going to get the solution after we evaluate a little bit. So let's find our a, b, and x. Remember, a is what's in the logarithm. What's in our logarithm is x, so a is equal to x. B is our base from up here. Our base is 1/3. And our x is what's on the other side of the equation, on the right side of the equation, and we have a -3. And as we know, we can rewrite our log into exponential form. So we take our base b, substitute it in there, we get 1/3. We substitute our x is -3, so -3 is our exponent, and that's equal to our a. And then the equation is equal to our a value. A is equal to x. So as I mentioned in my other videos as well, once you get more comfortable just changing things from logarithmic form into exponential form, you really can skip this little step here. This is just to help you kind of ease into it, but you know, this isn't necessary. You don't have to write this part either, because hey, if you just keep practicing, you get some more studying in, you'll be okay with changing things from log form to exponential form and back the other way too. Sometimes we want to do that. So now we're just at a point where we need to evaluate this equation. We literally have x by itself. X is what we're looking for, and whatever 1/3 to the -3rd power is, that's a solution. Remember, with exponents that are negative, we wrote that down right there. If we have a negative exponent, that's going to force the reciprocal of the base, okay, and then it's going to change the exponent from negative to positive. So this is generally how it looks, but so I went ahead and wrote a more general representation of the property that we need to be using right now. If we have any fraction that's raised to a negative power, what it does is it gives the reciprocal of the fraction. So instead of x over y, it's y over x. They flip. And then instead of a negative a, whatever that number is, you turn it to a positive a. And that a will be applied to everything in your numerator and denominator. So it just ends up looking like that. If we apply that same property here, then 1/3 to the -3rd power will become 3 over 1. Remember, we're going to take the reciprocal of 1/3, we're going to flip it, so 1 over 3 becomes 3 over 1, and then this exponent here will change from a -3 to a +3, and that +3 will be on both the numerator and denominator. So then from here, x is equal to 3 to the 3rd over 1 to the 3rd. Well, 1 to the 3rd, 1 times itself, 3 times is just 1. If we divide anything by 1, we don't need it, we wouldn't write it. So this really just becomes 3 to the 3rd power. So 3 to the 3rd, as we wrote up here, is 27. So our x is 27. Log base 1/3 of 27 is equal to -3. So for this next one, we want to find a, b, and x. Find our a, find our b, and find our x. A is what's inside the log here. what we have in the log is x, so a is equal to x. Our b is 5 because that's the base of the logarithm. And our x is what the logarithm is equal to, which in this case is 0. The goal of identifying these variables is to change this into exponential form because logarithms and exponents are inverse operations. This is why all this is working the way it is. I go more into detail into that in the other video, but really what you need to know is that logarithms undo exponential form, and anything in exponential form can be undone by a logarithm. So we take our b, substitute it in, that gives us 5 as our base. Our x is 0 in this case, so we substitute in 0 for x, and that's equal to our a. Our a is equal to x. So once again, here, if what you're solving for is in the logarithm, moving into exponential form is going to solve the equation. It undoes the logarithm. It's an inverse operation. So check it. We just have x equal to 5 to the 0 power. So as we remember from our exponent properties, anything to the power of 0 is equal to 1. So 5 to the 0 power is 1, and we have solved our equation. So there's one more example I want to do. Let's move down a little bit. For this one, we have a natural log. Remember, the ln, when you see that, the way you say it is natural log. So I feel it's more helpful if when you're getting introduced to all this, you really work hard on the definitions and how you talk about these things even in your head. Because if you just say ln, that doesn't have as much meaning as if you're saying the natural log, because that's really what this represents. And what we need to remember is what the base of natural log is. Because remember, we need to find a, b, and x. Just going with what we do know, we remember that a is what's inside the logarithm. So it's inside our logarithm is e to the 5th power. We'll just come back to b here in a minute. Let's go ahead and see the other thing that we actually know. Our x is, just x. Because our x, remember, up here at the top in logarithmic form is just what the equation is equal to. Our equation is equal to x. So x is x, but what's our base? What is the base of a natural log? What is it? Remember from our properties video, if we ever see the natural log of x, we know that the base, we just don't write it, is e. The base of a natural log is always e. So we know that our b value must be equal to e. Let's change this into exponential form and see where it gets us. Our b is e, so we substitute that in. Our x is x, so we're just going to substitute that x in. And our a is e to the 5th power. Now here, we don't have the solution just nice set up for us like it is in these other equations, but really that makes sense. We're not looking for what's in the logarithm, so exponential form isn't going to undo everything. We're looking for what this natural log is. We're evaluating this. So take a look at what we have. E to the x power equals e to the 5th. What is the base? The base is the same. E is a number. E is a number. So if we have e to the power of x equals e to the power of 5, and we know these are equal because that's what the equal sign means, is that what's on one side is the exact same as what's on the other. What do we know x has to be? X must be equal to 5. Our exponents must match if our bases are the same. So that's how we can solve some basic log equations using just the definition of logarithm and a little bit of number sense. Hopefully you found this helpful. If you did, please like and subscribe and comment. Leave me some feedback. If you like this video better, let me know. If you like my inverse video better, let me know. Mr. Otwell out. Peace. So we want to solve some because logarithms and exponential